implemented in real life situations. I talked about you having a single computer and or maybe input device and a single output device. In that case, what are the steps that need to be followed in order to manage colors between your input and output devices, right? So just as a method to recap, what are the three steps that needed to be followed? The first one being calibration. Calibration in some sense is linearization of the TVI response of output devices, right? So that is what calibration is. The second was characterization. Characterization was done with the help of some output test charts, output device print test charts, and with the help of some characterization data. And ultimately the last part was conversion, where after characterization was done, then for any unknown input data, we could use this characterization data, and ultimately the profile, the color profile that was developed using this characterization data, in order to convert colors so that there is equivalency in terms of color appearance between input and output devices, right? So these are the main areas that we talked about in the previous lecture. And we also saw when we are dealing with device dependent color management, you see, if there are n number of input devices and n number of output devices, then the total number of such conversions that needed to be done, or total number of color management protocols that needed to be followed, was n into m. So if you have 3 input devices and 3 output devices, then total number of conversions were 9. So this was a cumbersome process because the larger the number of input or output devices that you have, or even if you change some of the output device, then you will notice that you have to do the entire process from scratch for those new devices that you have replaced or new devices that you have added, right? So in order to so we have a more efficient method to achieve color management for for cases where we are using multiple input and multiple output devices. So today we will be talking about that. This is basically known as closed loop or device independent color management. This will be familiar to the basic idea or the schematics of color management that I talked about to the in one of the, I think in lecture 12, I think I talked about the schematics of color management. So you will find that we use the same exact principle while dealing with managing colors when we have multiple input and output devices. So consider a big newspaper organization who is having photographers and news journalists, photojournalists spread across the length and breadth of the country as well as different parts of the world. So for them, and of course they have multiple printing machines as well in different locations. So for them, if they needed to manage colors between their input, that is between the camera, and the output, that is the offset printing machine, they would have, if we would have followed device dependent color management technique, then we would have required managing colors between pairs of devices. So that would incrementally increase the complexity of the problem, and the total number of color managing protocols that we needed to follow would have been n into n, right? But what if there is a more efficient method of doing it? So today we will be, in this lecture we will be discussing about the most commonly used and industry standard in management of color that is being used today, which is known as device independent color management. So we know what device dependent and what device independent color spaces are. So what is a device independent color space? If I ask you, Device independent color spaces are those where the values do not the colorimetric values do not depend upon device or do not vary from one device to the other or one platform to the other. What they do is, what is being done is, they have these values are obtained as a manifestation of your yeah, how colors are perceived by the human population in general. So they are absolute values, they do not change for devices, they do not change for manufacturers, they do not change for any viewing platform. So one example of such device independent color space is XYZ, as I already mentioned, and also LAB, and there are so many others. So our focus here would be to consider this particular picture that we have on the left. Okay, I think I have a better picture than this. Yeah, this one. So let us consider this particular image over here. This is your camera, which is an input device. This is a monitor again, which is your output device, if you are using a camera in that sense. So this is a digital printer, which is again an output device, and this is your offset printer, which is your output device. So in this context, in this picture, you see there are multiple input devices and multiple output devices. Now in order to manage colors between them, when I say managing colors between these devices, what I mean is, in order to bring equivalency of color appearance between images that are created or reproduced across all these devices, we need what is known as device independent color space. What is actually done is, so for example, in the previous lecture, as I told you, you have an input device, let us say it's a camera, and an output device, let us say it's a offset printer. What the first thing that we needed to do was calibrating that particular output device or the printer in order to get the basic working state, or get some information on the basic working state of that particular printer. Following which, we used a output device, output test target. In our case, for offset printers, what we commonly use is the IT 8.7/3 test target. We print it. Along with that test target, we also have a characterization data. Characterization data tells us what the colorimetric value for each of the patch in the output test dart should have been. So after printing, we do not get exactly those data which we were supposed to get. What we get is the actual colorimetric value. We can measure it using a colorimeter or spectrophotometer. So once we have printed this and we have measured it, what we need to do is, we need to create a lookup table. The lookup table will contain what, on one hand, on the left hand side, it will contain what the colors were supposed to be, and on the right hand side will have what the colors are. So once we have this data, we can convert any unknown data using this particular LUT, which is being put inside of a color profile. This has already been mentioned over there. Now you see, in the previous case, what we did was, just a second, let me just I'll just show you an example so that it is clear. Is it working or not? Let me see. Yeah, so it's open now. Here. So in the previous case, what we saw is, we created the conversion, that is what we were supposed to get, that is the characterization data, CMYK data, and what we are actually getting that. So essentially what we are doing, we are converting one device dependent color space to the other device dependent color space. This is not a color space transformation, mind you. This is not a color space transformation. This is only a lookup table This is only a lookup table. Okay, so this is not a color space transformation. You cannot convert CMYK to CMYK. You cannot convert CMYK to RGB. You cannot convert RGB to CMYK without first converting them to a device independent color space. So this is the basic information. Now the basic difference between a device dependent color management and device independent color management is the fact that as you can see in this particular picture over here, that suppose this is your digital camera which is working as an input device. So what will be the color space of the images that are taken using this digital camera? They will be RGB color space, right? Now, so for example, this is okay, I'll talk about it later on. So this is the image over here will be in RGB color space, right? Now instead of if your intention is to directly print this a particular image that you have shot on this camera in using your offset printer, in case of color device dependent color management, what we saw, we first calibrated this, then the 3 C's, right? We operated on the principle of the 3 C's. The 3 C's remain the same in this case also, but I'm just explaining you the basic difference between the device dependent and device independent color management protocols. Now in this case, if you want, the question is, the scenario is, if you want to print the image that you have shot using a digital camera using this particular offset multicolor offset printer, you would have converted this RGB, the image which is in RGB color space, to this CMYK color space using these conversion formulas, right? Using these conversion formulas that you have prepared. But in case of device independent color management, what we do is first we convert the input image from its native or embedded input color space to some device independent color space, right? So if you consider you have shot a digital image using this digital camera, so here the image is in RGB format, RGB color space. Instead of directly converting the colors into CMYK, mind you, using LUTs, there is no such color space transformation formula for directly converting RGB to CMYK. What I am trying to explain here is, in case of device dependent color management, you are converting colors using LUTs, not color space transformation. This is a very important distinction that you need to follow. Okay. So what in this case what we do is basically we convert the RGB color space into a device with RGB color space is a device dependent color space. We convert the image from RGB color space to a image in the device independent color space. So this may be XYZ, this may be LAB, whatever is required at a particular for the particular purpose. We choose that device independent color space, right? So we convert the images that are in RGB color space to a device independent color space, that is XYZ or LAB. So similarly, a image that you might have edited or you might have prepared using this monitor, again this is in a different RGB color space. So let us say for the camera, this is RGB color space 1, this is RGB color space 2. Similarly, for a scanner you have RGB color space 3. So these are all your input color spaces. So you convert all these images that you get from all these input devices from their native or embedded device dependent color space into a device independent color space, right? Now what happens, in the first slide when we talked about in lecture 12, I think 12 or 11, where we talked about the schematics of color management, what did we see? We needed to convert color spaces from device dependent color space to device independent color space before converting them back into another device dependent color space. Now take a look at this particular picture here. So we have an input device where the images are in particular RGB color space. So from here the RGB is a device dependent color space, we are converting it into device independent color space, and from here we are converting them back into another, that is the output color space, which is again a device dependent color space, right? So why do we do this? In this case also we are seeing that the input devices, input color spaces, we are converting the input color spaces into device independent color space, and from here we are again converting them back into, this is, let us say, a digital printer, hence it will have a CMYK color space number 1. This is a inkjet printer, a different CMYK color space 2. This is a offset printer, a different CMYK color space. So essentially what we are seeing is we are converting, this is the same as that lecture actually, you try to correlate between the two. So input profile, input color spaces are being converted, which are again device dependent color spaces, are converted into device independent color space, either XYZ or LAB, and then from here on these data are then converted back into CMYK color spaces, particular CMYK color spaces, which using which we will be able to print that particular image. So advantage, what are the advantages of this process? Advantage number 1 is, you see, here to count the total number of color space transformations that you have to make. In the previous case, how many transformation, in case of device dependent color spaces, how many color space transformations you needed to make for n? If you had n number of input device and n number of output device, total how many number of color space transformations you needed to make? M into n, or n into m. But in this case, total how many number of color space transformations you need to make? Count 1, 2, 3, 4, 5, 6. So total how many devices are there? There are 6 devices, 3 input device and 3 output device. So for this, if we are applying device independent color management protocols, then total number of color space transformation is how much? 6. How did I get? 3 plus 3. So if you have m number of input device and n number of output device, total number of color space transformation while doing device independent color management will be m plus n, right? So essentially your complexity of color space transformation and all these color management protocols is reduced to a great extent, because there you are in case of device dependent color space color management, you have to multiply the total number of color space transformations. Here you have to add the total number of color space transformations. So this is the first advantage. Also the second advantage, I have already, I think, given you a brief idea while talking about the schematics of color management. What was that? If our intention is to bring equivalency of color appearance or color constancy between input and output devices, we need to preserve the RGB values in that we are getting from input devices. So for example, here we have a monitor, scanner and a camera. So these are the sources of our RGB data, right? So we'll get images, digital images from all 3 devices, all 3 input devices, and we will have what is essentially known as the input color spaces. So we'll get RGB data from all these particular input devices, right? So the advantage of using this device independent color space is the fact that we will be, as soon as we are converting the RGB images from RGB color space, that is a device dependent color space, to a device independent, that is XYZ or LAB color space, we are preserving the RGB data. We are freezing, as I told you, as I mentioned, as I used this term previously also in that lecture, that we are preserving this RGB data. So what is going to happen if we are preserving the RGB data? What advantage do I have? So the advantage is, if our XYZ data, that is this particular data, is a manifestation of this RGB data. So as soon as we are converting this XYZ data to a CMYK data, so the CMYK data becomes a manifestation of that particular RGB. So if we are saying that from the monitor, the image that we are getting, that is in RGB2 color space, we have converted them into XYZ color space first, then again we have converted them from XYZ color space to CMYK2 color space, which is that of a inkjet printer, right? So this CMYK2 image will be a manifestation of the RGB2 color space or RGB2 data. And since why it will be manifestation of, because a CMYK data ta koththeke elo, it is coming from this XYZ value. এই XYZ ভ্যালুটা কোথা থেকে এলো? এই RGB data থেকে আসছে. So this XYZ data is a manifestation of RGB data, and in extension the CMYK data is a manifestation of this RGB data. So if that is the case, if the CMYK data is a manifestation of the frozen or preserved RGB data, that means the CMYK image will have a visual similarity or visual parity or equivalency in color appearance or color constancy with the RGB image. ঠিক আছে, তা সিএমআইকে ডেটা আসছে কোথা থেকে? XYZ থেকে। XYZটা কি না, ফ্রোজেন বা প্রিজার্ভড আরজিবি ডেটা, ঠিক কি না? তো সেটাই যদি হয় তাহলে সিএমআইকে ডেটার সাথে আরজিবি ডেটার একটা মিল থাকবে। তাহলে মিল থাকা মানে কি? তাহলে দুটো কালারের মধ্যে, মানে মনিটরের যে কালারগুলো আর প্রিন্টেড আউটপুটের যে কালারটা, তার মধ্যে একটা ভিজুয়াল সিমিলারিটি বা ভিজুয়াল প্যারিটি থাকবে, ঠিক আছে? সো দিস ইজ হোয়াট this is how device independent color space color management is basically done. So okay, so before going into this color management elements, I think I need to talk a little bit about profiles and how this thing is actually done. So we'll be talking about that in the next lecture. Okay.